According to the National Electrical Code, specifically NEC 810.20a, all metallic masts and supporting structures exceeding 6 feet in height are required to be grounded. This requirement applies to metal poles used to support satellite dishes. The responsibility for grounding the pole typically falls on the satellite dish installation company. They are expected to ensure that the pole is properly grounded and connected to the home's electrical service. The process of grounding the pole generally involves several steps. Firstly, a grounding clamp is attached to the metal pole. Secondly, a grounding conductor, which is typically a copper-clad steel or solid copper wire, is connected to the grounding clamp. Thirdly, this grounding conductor is then connected to the home's grounding electrode system, which is usually located at the electrical panel. Failure to ground the pole can create a significant safety hazard. If the pole is not grounded, it can become energized during a lightning strike or due to another electrical fault. This energized pole could then pose a shock hazard to anyone who comes into contact with it or the satellite dish mounted on it. There are a few additional considerations to keep in mind regarding grounding. Firstly, the grounding conductor must be sized according to the NEC requirements, which depend on the size of the pole. Secondly, the grounding electrode system should be tested to ensure that it is providing a proper ground. This test verifies that the system is effectively dissipating electrical faults. Thirdly, if the home does not already have a grounding electrode system, the satellite dish installation company may be required to install one. The purpose of a grounding electrode system is to provide a low impedance path for fault current to flow back to the source, which helps to trip a circuit breaker or fuse and to energize the circuit. The grounding electrode system typically consists of a ground rod, a ground plate, or a metallic water pipe that is in direct contact with the earth for at least 10 feet. The size of the grounding conductor is determined by NEC Table 250.122, which correlates the size of the overcurrent protection device protecting the circuit to the required size of the grounding conductor. For example, if the overcurrent protection device is rated at 20 amps, the grounding conductor must be at least 12 American wire gauge copper or 10 American wire gauge aluminum. If the overcurrent protection device is rated at 60 amps, the grounding conductor must be at least 10 American wire gauge copper or 8 American wire gauge aluminum. It is important to note that the grounding conductor must be continuous and without splices or joints. Any splices or joints in the grounding conductor can increase the impedance of the grounding path and reduce its effectiveness. The grounding electrode must be installed in accordance with NEC section 250.52. This section specifies the types of electrodes that are permitted, as well as the installation requirements for each type. For example, a ground rod must be at least 8 feet long and must be driven into the ground at least 8 feet. A ground plate must be at least 2 square feet in area and must be buried at least 30 inches below the surface of the earth. A metallic water pipe must be in direct contact with the earth for at least 10 feet and must be electrically continuous. In summary, the metal pole supporting the satellite dish must be grounded to ensure safety. The satellite dish installation company is typically responsible for grounding the pole, but it is essential to verify that the grounding has been done correctly. Proper grounding is critical to protect people and equipment from electrical shock and damage. A ground rod is a copper or copper-clad steel rod that is driven into the earth to provide a path for electrical current to flow in the event of a fault. The NEC requires that ground rods be at least 8 feet long and 5/8 inch in diameter. They must be driven into the earth so that at least 8 feet of the rod is in contact with the soil. Ground rods are typically installed near the electrical service panel and are connected to the grounding electrode conductor. A ground plate is a copper or copper-clad steel plate that is buried in the earth to provide a path for electrical current to flow in the event of a fault. The NEC requires that ground plates be at least 2 square feet in area and buried at least 30 inches below the surface of the earth. Ground plates are typically installed in areas where the soil is not suitable for ground rods, such as rocky or sandy soil. A metallic water pipe can be used as a grounding electrode if it is in direct contact with the earth for at least 10 feet and is electrically continuous. The NEC requires that the water pipe be bonded to the electrical service panel with a bonding jumper. The bonding jumper must be sized according to NEC Table 250.66. If a metallic water pipe is used as a grounding electrode, it must be supplemented by an additional grounding electrode, such as a ground rod or a ground plate. This is to ensure that there is a reliable grounding path in the event that the water pipe is disconnected or becomes corroded. The grounding electrode conductor is a conductor that connects the grounding electrode to the electrical service panel. The NEC requires that the grounding electrode conductor be sized according to NEC Table 250.66. The size of the grounding electrode conductor depends on the size of the service entrance conductors. For example, if the service entrance conductors are 4/0 American wire gauge copper, the grounding electrode conductor must be at least 2 American wire gauge copper. The grounding electrode conductor must be securely connected to the grounding electrode in the electrical service panel. The connections must be made with approved connectors and must be protected from corrosion. In addition to grounding the metal poles supporting the satellite dish, it is also important to ground the satellite dish itself. The NEC requires that all exposed metal parts of electrical equipment be grounded. This includes the metal parts of the satellite dish. Grounding the satellite dish helps to protect people from electrical shock and also helps to protect the satellite dish from damage due to lightning strikes. The satellite dish can be grounded by connecting it to the grounding electrode system with a grounding conductor. The grounding conductor must be sized according to NEC Table 250.122. The grounding conductor must be securely connected to the satellite dish and the grounding electrode system. The connections must be made with approved connectors and must be protected from corrosion. It is important to note that the grounding requirements for satellite dishes can vary depending on the local electrical codes. It is always best to consult with a qualified electrician to ensure that the satellite dish is properly grounded. When grounding a satellite dish, it is crucial to use approved grounding clamps and connectors. These components are designed to provide a secure and reliable connection between the grounding conductor and the metal parts of the satellite dish and the grounding electrode system. Using non-approved clamps and connectors can lead to loose connections, corrosion, and ultimately, a failure of the grounding system. Grounding clamps are typically made of copper or brass and are designed to clamp onto the metal parts of the satellite dish and the grounding electrode. They should be sized appropriately for the grounding conductor being used. Grounding connectors are used to connect the grounding conductor to the grounding electrode system. They are typically made of copper or brass and are designed to provide a secure and reliable connection. It is important to choose grounding connectors that are compatible with the type of grounding electrode being used. In addition to using approved grounding clamps and connectors, it is also important to protect the grounding conductor from physical damage. The grounding conductor should be run in a conduit or other protective covering to prevent it from being damaged by lawnmowers, weed whackers, or other equipment. The grounding conductor should also be protected from corrosion. The grounding conductor should be made of corrosion-resistant material, such as copper or copper-clad steel. The connections between the grounding conductor and the metal parts of the satellite dish and the grounding electrode system should be protected from corrosion with a corrosion-inhibiting compound. Regular inspection and maintenance of the grounding system are essential to ensure that it is functioning properly. The grounding connections should be inspected periodically for looseness, corrosion, and damage. Any loose connections should be tightened, and any corroded or damaged components should be replaced. The grounding electrode system should also be tested periodically to ensure that it is providing a proper ground. The test can be performed by a qualified electrician using a ground resistance meter. The ground resistance meter measures the resistance of the grounding system to earth. A low resistance reading indicates that the grounding system is functioning properly. A high resistance reading indicates that the grounding system is not functioning properly and needs to be repaired. Lightning protection systems are designed to protect structures from damage caused by lightning strikes. A lightning protection system typically consists of air terminals, conductors, and a grounding electrode system. Air terminals are metal rods that are installed on the roof of a structure to intercept lightning strikes. The conductors are wires that connect the air terminals to the grounding electrode system. The grounding electrode system provides a path for the lightning current to flow to ground. While grounding a satellite dish pole helps to minimize the risk of damage from electrical faults and indirect lightning strikes, it's important to understand that it does not provide complete protection from direct lightning strikes. For comprehensive lightning protection, a dedicated lightning protection system should be installed. This system would include air terminals, lightning rods, and the structure connected to a network of conductors that lead to a separate grounding electrode system. This specialized system is designed to safely channel the immense energy of a direct lightning strike to ground, minimizing damage to the structure and its contents. Remember, proper grounding and, if necessary, a dedicated lightning protection system are crucial for ensuring the safety of people and property. Always consult with qualified professionals for installation and maintenance of these systems. Understanding the principles of grounding and bonding is essential for electrical safety. Grounding is the process of connecting electrical equipment to the earth, providing a low impedance path for fault current to flow back to the source. Bonding is the process of connecting all metal parts of an electrical system together, creating an electrically continuous path. Grounding and bonding work together to protect people from electrical shock and to protect equipment from damage due to electrical faults. The NEC contains detailed requirements for grounding and bonding. These requirements are designed to ensure that electrical systems are installed and maintained safely. It is important to consult the NEC and to follow all applicable requirements when installing or working on electrical systems. If you are not familiar with electrical codes and safety practices, it is always best to consult with a qualified electrician. An electrician can ensure that your electrical system is installed and maintained safely and in compliance with all applicable codes.